Hey everyone and welcome. Today we're going to roll up our sleeves and tackle a real classic in rotational dynamics. It's a problem from a textbook that has been a benchmark for physics students for decades. So let's just dive right in.
So, if you're into physics, you've probably heard of I.E. Irodov's problems in general physics. It's kind of legendary, a real rite of passage. These aren't just plug-and-chug problems. They're designed to make you think, to really build a deep, physical intuition for how the world works. And today, we're taking on one of the classics, Problem 1.48, a really fascinating one about deceleration.
And here it is, in all its glory. So you've got this solid body, and it's slowing down. But, and this is the key, it's not slowing down at a constant rate. Its angular deceleration, which is beta, is proportional to the square root of its angular velocity, omega. Our job? Find the average angular velocity over the entire time it takes to go from its initial speed all the way down to a complete stop.
Okay, so with any physics problem like this, the first and probably most important step is to translate all those words into the language we can actually work with, math. We need to turn that physical description into a concrete equation we can solve.
So just think for a second. What's the most fundamental link between acceleration and velocity? How do we actually define that relationship with math?
That's it, right? It's the derivative. Angular acceleration, which we're calling beta here, is just the rate of change of angular velocity, omega, with respect to time. This is our foundation, our main tool for this problem.
All right, now we just combine that definition with what the problem tells us. We know that deceleration is proportional to the square root of omega. So that means d omega by dt equals some proportionality constant, let's just call it k, times the square root of omega. And super important, we've got to put a negative sign in there because the body is decelerating, its angular velocity is going down.
Perfect. We've got our differential equation. Now we're ready to start what I like to call the calculus journey. We're going to break this thing down and solve it, step by step, to find that average velocity.
You know, a good physicist always has a plan of attack. Here's ours. First, we're going to solve that differential equation to get a formula for omega at any time t. Then, second, we'll use that formula to figure out exactly how long it takes for the body to come to a full stop. We'll call that time capital T. And finally, we'll take both of those results to calculate the average angular velocity. It's a nice, clean roadmap.
Let's get started with step one. We've got our equation, and the classic way to solve this is a technique called separation of variables. Basically, we just want to get all the omega stuff on one side and all the time stuff on the other. So we'll divide by the square root of omega, multiply by dt, and we're good to go. Now that our variables are separated, we can integrate both sides. And we're going to use a definite integral here. So on the left, we'll integrate from our initial angular velocity, omega naught, up to some later velocity, omega. And on the right, we'll integrate from our start time, which is t equals 0, to that corresponding later time, t. Actually, doing the integration here is pretty straightforward. The integral of omega to the negative 1/2 power is just 2 times the square root of omega, and the integral of negative k is just negative kt. We plug in our limits of integration, and we get our result. 2 root omega minus 2 root omega naught equals negative kt. Now for a little bit of algebra. We just rearrange those terms to solve for omega. And voila! We have our first big result. This equation tells us the angular velocity at any moment in time. This is the key that's going to unlock the rest of the problem for us. Okay, on to step 2. We have this awesome function for velocity. So how do we use it to find out how long the body actually keeps spinning before it stops?
Well, stopping is pretty simple, right? It just means the angular velocity is 0. So we take our omega of t function, set it equal to 0, and then we solve for the time, which we're now calling capital T. The algebra's nice and quick, and it gives us the total time of rotation. T equals 2 times the square root of omega naught, all divided by k. Step 2, done.
All right, finally step 3. We need to find the average velocity. Let's just go back to the fundamental definition. The average value of any function over an interval is just 1 over the length of that interval times the integral of the function over that same interval. We have our function, and we have our interval. So now we just plug in the pieces we've already found. We substitute our expression for t out front. Notice we flipped it because it's 1 over t, and we plug our function for omega of t right inside the integral. I know it might look a little messy, but really we're just putting together the puzzle pieces we already built. And now for the last big step. We just have to evaluate this integral. It's a pretty standard use substitution, and it gives us this expression that we now need to evaluate from 0 to t. We are on the home stretch now. After all that calculus, we've arrived at the moment of truth. Let's plug in those limits, see what we get, and most importantly, figure out what this answer actually tells us about the physics of what's happening.
And here's where you see the real beauty of physics. After you plug everything in, and all the dust settles, all the K's and T's, they all cancel out. And we are left with this incredibly simple, elegant result. The average angular velocity is just the initial angular velocity divided by 3.
But wait a second, your intuition might be screaming at you right now. I mean, if it starts at omega naught and ends at 0, shouldn't the average just be half of that? Shouldn't it be omega naught over 2? This is where the physics gets really, really cool. And the reason is that our deceleration is not linear. If it was constant, then yes, the velocity would drop in a perfect straight line and the average would absolutely be omega naught over 2. But in our problem, the deceleration is proportional to the square root of the velocity. What that means is, it decelerates fast when it's going fast, but it decelerates really slowly when it's already going slow.
And that's the whole point. Because the deceleration gets weaker and weaker as the body slows down, the body spends much more time rotating at those lower speeds. It kind of lingers at the bottom end of its speed range before it finally stops. All that extra time spent at low speeds pulls the overall average down, way below that simple midpoint of omega naught over 2, all the way to omega naught over 3.
So that just leaves us with one final thought. This type of relationship, where the rate of change depends on the square root of the quantity itself, it's not just some random math thing. It pops up in other places in physics. Think about water draining from a tank, which is described by Torricelli's law. What other systems can you think of where the same kind of physics might be at play? Thanks for joining me on this one.